In this video, we're going to actually start using the chain rule. You're likely getting bored of seeing this opening screen, the chain rule written out, displayed at the beginning of these last couple of videos, but here we go. This is, again, what we've been looking at for the last couple of videos. We're going to start with some examples here. So this says we're going to start with some basic examples. Let's not get too ahead of ourselves, though. There's still going to be some difficulty here, and the difficulty is going to lie in identifying the pieces that are involved in the chain rule. We have to be able to decompose these functions into inside and outside pieces. So if you want, go back a couple of videos when we talked about introducing composition in the chain rule here to see if you can remember those examples where we did that decomposition. You might recognize some of these kinds of examples from there. What we're going to do is we're going to try to identify the inside piece here. Then, after we identify the inside piece, we're going to differentiate the rest, pretending that the inside piece is just a variable. Now really it's going to be like a function, but that's okay. Then we'll multiply by the derivative of whatever we identified as the inside piece. So what that means is that for this square root function, we could identify x squared minus 2 as the inside piece. In my classes, sometimes we'll put a box around these things. And what we could do is rewrite this derivative expression. We can say this is really the derivative of some empty box. And now what we want to do is differentiate the rest of the function. Well, we have a square root, right? So this is really the derivative of some empty box here with some stuff in it raised to the half. And now we can say, oh, let's do the power rule. Let's bring this half out front, subtract 1. So this is going to be half times this box raised to the negative half. And then we're going to multiply by, sometimes we'll call this thing box prime. And now we can just fill in the pieces, right? What goes in the box? Well, we said this was x squared minus 2. And the derivative of that, well, that's going to be 2x. Similarly, we could go ahead and say all this stuff inside of our sine function, we could wrap up in a box. And we could rewrite this as the derivative of sine of a box. And now we'll just pretend that this is all fine and normal, and we'll differentiate this. We'll say, okay, the derivative of the sine function, that's cosine of our box. But then what we need to do is multiply by our box prime, the derivative of the box. And again, now we can say what was in the box. Well, it was 4x squared plus pi. And so the derivative of that is 8x. And we could do some work rewriting these and things like that. But what we're going to do is redo these examples a little bit more formally. When we identify that inside piece, instead of using a box, we're going to use u equals some stuff. And then we're going to have some sort of a function of u that we can differentiate. And the chain rule says that that's the derivative with regard to u times the derivative of u with regard to x. That's our derivative of the inside piece. So we'll write this out a little bit more formally just to see how this goes. But informally, this little box notation I think is kind of quick and easy and hopefully pretty visual. All right, so let's go ahead and do our variable substitution. We'll say u is going to be the inside piece. That's x squared minus 2. So this is suddenly the derivative of, maybe I'll write this as u raised to the 1/2. I'll just quick write it in that power notation. Now I can say the chain rule since these two things are different from each other, says that this is going to be the derivative. Maybe I'll use this red. No, I'll use it in black. Sorry. The derivative with regard to u of u to the 1/2 times the derivative with regard to x of u. We'll do our power rule now just like we did earlier, and we can say this is 1/2 times u to the -1/2 times the derivative of u with regard to x. That's going to be 2x. And so we've got 1/2 times x squared minus 2 to the -1/2 times 2x. We can do some rewriting here. This 2x times 1/2 is really x. My negative exponent is going to go into the denominator. We've got a square root of x squared minus 2. That is our derivative using the chain rule. Okay, go ahead and see if you can try this next one. We've already seen what it's going to be, but use this variable substitution. Set u equal to 4x squared plus pi here, and see if we can follow out the same kind of steps to differentiate this composite function. Pause the video and see if that goes well. All right, hopefully you're back. This is the derivative with regard to x of sine of u. Maybe I'll put that in parentheses so we know that's inside of our sine function. And the chain rule says that that's going to be the derivative with regard to u of sine of u times the derivative with regard to x of u. So the derivative of this sine function is going to be, oops, I'll move this over here, is going to be the cosine function. And again, we can say the derivative of this u stuff is going to be 8x. And I'll put that in black. So now we can rewrite this as 8x times cosine of 4x squared plus pi, where again, that was u, and this stuff here in front is the derivative of u, the inside piece. That is our derivative of this sine function using the chain rule. All right, here's a couple more examples. See if you can pause this and give a shot at it. I'm going to rewrite this one for you just so you can see how it looks. This is really 4 times the tangent of x function raised to the -1/3, right? This cube root of the tangent of x function in the denominator. So it's a negative exponent in the denominator, and it's a 1/3 exponent for the cube root. Similarly, this we can rewrite. That really means cosine of x squared. So when the squaring is on the cosine function, it means that we're squaring cosine of x. So see if you can identify the inside piece here, the u part. If you want to use the box notation just to get a feel for it, that should be fine. But hopefully that will go pretty well for you. I'd encourage you to pause the video and try those on your own. All right, so I've got a start on both of these. So I picked this tangent function as the inside piece because it's in this power function. So we rewrite this with 4u to the -1/3. And so what we're really going to do is differentiate that with regard to u and then differentiate u with regard to x. Power rule says bring the -1/3 out. We have -4/3 times u to the -4/3 times the derivative of tangent of x. That's secant squared. So now what we can do is rewrite this. We can say this is -4 secant squared x over u to the 4/3. So I'll call this tangent to the 4/3 x. And that's what we've got. We might be able to do some trig stuff on here to simplify that, but let's just leave it there for now. Similarly, we identify the cosine function as the inside piece here. And so we look at the derivative of u squared with regard to u multiplied by the derivative of u with regard to x to link these rates of change together. Nice easy power function. Bring the 2 out front, so we have 2u times the derivative of the cosine function. That's negative sine of x. So all this to say we have -2 cosine x sine x. And again, there's some like trig identities that you could probably use to rewrite this in different forms, but let's just leave it like this for now. That's how we differentiate these functions. All right, when we step up in difficulty, we can add different layers of composition. Maybe instead of just one function inside of another, maybe we have multiple functions inside of things. Let's rewrite this just so we can see what this really looks like. This is the derivative of e raised to the sine of x squared plus 1 function raised to the 4th. That's what this is. Whew! There's lots of stuff going on there. What we'll notice, if we're using boxes here, we can notice all of this stuff inside of this exponential function. But then we'll notice that this sine function is inside of a power function raised to the 4th. But then look at this. X squared plus 1 is inside of the sine function. So we've got like little nested Russian dolls here. We got lots of different layers of composition. So let's go ahead and see if we can use some variable substitutions to deal with this. We're going to call u sine of x squared plus 1 raised to the 4th. And then we're going to call the blue one, maybe we'll call it v. That's just sine of x squared plus 1. And then the green one, I'm up to w. I'll call that x squared plus 1. So I'm just labeling all of my layers of integration. Now what we're going to notice is that this is going to be the derivative with regard to u of e raised to the sine of the 4th x squared plus 1. Maybe I'll say e to the u. That's easier. Times du over dx. But what you'll notice is that du over dx is really going to be du over dv times dv over dx. Maybe I'll do that one in blue. But dv over dx is really going to be dv over dw times dw over dx. Okay, so let's rewrite these. This is really v to the 4th. V is really sine of w, and w is x squared plus 1. We should be able to differentiate all of these pretty easily. Okay, the derivative of e to the u with regard to u, that's no big deal, right? All that is e to the u again. So let me keep my colors straight. I've got e to the u. Then I'm going to multiply this by the derivative of v to the 4. That's 4 times v cubed multiplied by the derivative of v. So that's going to be cosine of w times the derivative of w with regard to x. That's 2x. So there's all these multiplication signs in between here. And now we can just substitute everything back. U is sine of x squared plus 1. So that means we've got e to the sine of x squared plus 1. Oh, and I forgot the 4th power on there when I said it. Raised to the 4th. Times 4 times v cubed. That's sine cubed of x squared plus 1. Times cosine of w. That's cosine of x squared plus 1. Times 2x. All right, so let's group all this stuff together and write it kind of nicely. There's not going to be a beautiful way of doing this, though. The 2x times 4, I'll bring that out front and call that 8x. Then I'm going to use my trig functions. Sine cubed x squared plus 1 times cosine x squared plus 1 times e raised to the sine of the 4th x squared plus 1. That's my derivative. Notice, though, when we color code these, it's really just the derivative of each link with regard to the stuff on the inside of it. I say just. There's a lot of work to get there. This is not a small problem. Here's another one that we've got. See if you can identify all of the different layers of composition on this. Try it on your own, and in a couple minutes, come back, and I'll set this up in pieces in a couple minutes when you come back, I'm going to have the layers of composition written out, and I'll have essentially this first line here. And then I'll let you go back and work on things a bit and see what we can do. All right, pause the video, come back in a minute. All right, here's what we've got. I've identified 3 different layers of composition that we have, labeled them all out, and then you'll notice I rewrote a couple of them, right? So u, I said, was the cotangent of e to the x squared minus 10, but if we said that v is e to the x squared, then we'll really call u cotangent of v minus 10. And if w is x squared, then v is really just e to the w. That's going to help us do the chain rule on these. Okay, so now things should go pretty well. We're just going to look at each piece and differentiate it with regard to whatever the variable is that's written here. So the derivative of this with regard to u is going to be 12 times u to the 11. Then when we multiply that by the derivative of u with regard to v, we're going to be looking at the derivative of the cotangent function. The derivative of tangent, you might remember, is secant squared. So the derivative of cotangent is going to be negative cosecant squared of v, and that constant negative 10 just goes to 0, so we don't have to worry about that. Then what we'll do is we'll multiply that by the derivative of v with regard to w, so that's e to the w, it stays the same. And then finally we have the derivative of w with regard to x, that's 2x. Now we can go ahead and just plop everything back into place, put u in for u, put v in for v, put w in for w, and we'll make sure that we have only x's left over. So we've got 12 times cotangent of e to the x squared minus 10 raised to the 11th power times negative cosecant squared of e to the x squared times e to the x squared times 2x. And now there's a lot of reorganizing and rewriting. I'll probably peel out this negative from the cosecant and put that out front with my coefficient. So I've got negative 24x. Then I'll maybe use my cotangent of e to the x squared minus 10 raised to the 11th power times cosecant of e to the x squared times e to the x squared. And I think I got everything then, right? Yeah, that's my derivative. Pretty ugly. But that's how the chain rule goes. We end up just multiplying these linking derivatives with each other. Remember those gears, right? We multiplied the rates of change relative to those next pieces. So that's the same kind of thing that we have going on here. Again, if you want to use these boxes with box primes, that works. But for stuff that's a little bit trickier, it really is nice to use those variable substitutions. Write things out as explicitly as we can and go slowly through it. One of the difficult things is identifying when to use the chain rule. Right? Noticing this composition, and then not only that, but being able to split things into the parts. Notice what all the layers of composition are. That does take a little bit of practice, so hopefully you'll be able to get used to that as you move through different examples of this. But once we start moving forward, we'll look at one more video where we just put a bunch of these derivative rules together, product rules, quotient rules, chain rules, all at the same time to really get a feel for them. And then we're going to move on to another way of differentiating things called implicit differentiation, which will use a lot of product and chain rules and things like that. So we got to make sure that we're really square on getting this derivative rule figured out, knowing how to differentiate these composite functions. Good luck as you move on. Try a bunch of examples. Doing this is really a good way of getting used to doing it. So I know that sounds silly, but make sure that you're practicing. All right, good luck.